Hey guys, this is Coach Brian going over your 4.3 notes. This is all about graphing logarithmic and exponential functions. We're going to jump right into this with our parent functions. We start off with our exponential parent function. Remember, it's a base to a power. In this case, we're going to be working with a base 2. And before we even start, we want to talk about critical points, which are kind of like the go-to points when you're starting a graph from its most basic parent form. And most of the time, in general, exponential critical points are going to be 0, 1, so that'll be a y-intercept, and 1 with the base, because whenever you raise the base number, whatever it is, any number, to 1, it will be itself. So in this case, when we have a 2 and we put in a 1, we get out a 2. Input, output. So that's in general, because it's not always, it could change, it's not absolute, but in general. So before we even start with, let's do some points. Let's put in some values and see what we get out. So again, these are our inputs. We want to see what we get out. And remember, this is the same thing as y, It's the same thing as y, which is your output. And it's what we get when we plug into our function. So if we did 2 to the negative 3 power, 2 to the negative 3, if you know your exponent rules, that 2 to the 3 would have to drop down into the denominator, and then 2 to the third is an eighth. So we would go negative 3 up an eighth. And so you can see we're already super close to that x-axis. If we put in a negative 2, we would get out 1 over 4. If we put in a negative 1, we'd get out a half. And so you can see the points just kind of slowly start creeping up. And then we put in a 0. Any number to the power of 0 is 1. So there's that first critical point we were talking about, 0, 1. Let's keep it going. 2 to the first is 2. There's that second critical point we were talking about. Put in a 1, get out the base. 2 squared is 4, 2 cubed is 8. So you can see that pretty quickly this graph starts sharply increasing. And then we would want to connect all our dots here with one smooth curve. One smooth curve, take 2. All right, and that graph would keep going up towards infinity. And then over here on the left side, it would presumably keep getting, if I could draw, keep getting closer and closer to our x-axis. So, x-intercepts. Pretty much what you'd be asking is, what number could I plug in here to get 0? Because that's where I would be crossing the x-intercept at 0. Have a height of 0, and there is no number that you can plug in there and get a 0. So there is no x-intercept. And our y-intercept, we already said, that's what you get when you put in a 0, and we can see right here that we put in a 0 and we got out a 1. Our domain, well, there's an arrow over here. I can chug along the x-axis. I don't have anything stopping me, nothing slowing me down. Presumably, I'm going to go on forever from negative infinity to positive infinity. And so we could write that as all real numbers, or in interval notation, we could say negative infinity to positive infinity. Range has to do with my y values, and so I never actually cross my x-axis. But I do go up forever towards infinity. So I would say that my range is from 0, not included, so it's parentheses, to infinity. Asymptotes. There's nothing like vertically keeping this graph in line right now, but it never goes beneath the x-axis. So I could say that I do have a horizontal asymptote. I remember HOY equals, so I would say y equals 0 is the equation of the horizontal line. Now our critical points, just like we said up here, our critical points are 0, 1, and then 1 and our base, which was 2. So this is our parent exponential function when the base is 2. It will change slightly if the base is different. If it was a 1 or a 3 or a 4 or any other number, it would change slightly, but in general, it's going to follow these guidelines. Let's jump to the logarithmic now. Logarithmic function is going to be log base. My input is currently the argument. Remember, that's called the argument. And then whatever we get out, is our y value. Remember, logs find unknown exponents. So when we're solving this, we're pretty much asking ourselves, if we drop cross, we're asking ourselves, what exponent, if I raise the base to this exponent, would match this argument, okay? So as we start graphing this, we would be plugging in our x's into the argument. So log base 2 of 0, log base 2 of 0. Again, think of this as asking yourself, 2 to what power would give me 0? And we just said up here, there is no answer. There is none. There's no number that will give me that value. And then we could ask ourselves here, 2 to what power gives me 1/8? Well, that would be the -3rd. 2 to what power gives me 1/4? That'd be -2. And I think you can probably start to see the pattern we got going on here. Bolden these up a little bit. All right, so now let's actually graph this and see what we've got. We said there was no exponent that could give us a 0 output, but when we put in 1/8, which I gotta zoom in super close here. When we put in 1/8, if you count this, it's 1, 2, 3, 4 dots between 0 and 1. So we would go between these dots to get 1/8. So 1/8 gave me an output of -3. So this is a point on my graph already super close to that y-axis. I put in a -2, or excuse me, I put in 1/4, I get out a -2. I put in 1/2, I get out a -1, so 1/2, -1, right in the middle. I put in 1, I get out 0. I put in 2, I got out 1. I put in 4, I got out 2. And just for one extra point here, if I was trying to see, what do I get when I put in an 8? I would be asking 2 to the what power equals 8, and so my output would be 3. So 4, 5, 6, 7, 8, up 3. So you can see this graph really starts to level off pretty quickly. It gets really close to this x-axis. It's got this upward curve, but it starts to more slowly increase. And then as we go down to this region of it, it would start to get super close to my x-axis, but not ever actually touch it. So the critical points, similar to our exponential graph, the critical points of this graph are 1, 0, and base, 1, which I realize now up here I apologize if you're a note taker. It should have been base. I'd put 2 because I was saying it as I was writing it. What I want you to notice is that these tables right here and here, these tables and these general points are inverses of one another. They are inverses of one another. All right, so after graphing our points, we want to see what the x-intercept and the y-intercept are. Well, our x is crossed right here at 1, 0. But we never actually cross the y-intercept. And we showed that here where we said there's no value that we could input to our logarithmic parent function that would get us to cross that y-intercept. Our domain, it's x values, remember? So on the x, they're never going past 0, and then they're going to the right forever. So our domain would be not including 0 to positive infinity. Our range, it's got an arrow pointing down, and even though it's leveling off, this graph is still going up forever and to the right forever, which we said in domain. But for range, we're really worried about the fact that it's going up and down forever, and we would call that all real numbers, or negative infinity to positive infinity. We did say that we have a vertical asymptote. VU x equals is how we can remember our vertical information, and it has an undefined slope, and in this case x equals 0 because it's our y-axis. Our critical points, referring to this box right here, were 1, 0, and our base, which if we go look, it was 2, and when we put in a 2, we got out 1. All right, so let's now look at some transformations. The transformation rules are very similar to what we've been learning since Algebra 2. Starting with our h, which we can locate here and here, that's going to determine our horizontal shifts. They do the opposite of what you would think. So when it's minus an h, that's going to move us to the right. And when it's plus h, that would move us to the left. That is the opposite of what you would expect. K determines our vertical shifts. It does exactly what you would expect. If it's plus k, that's up, and if it's minus k, that's down. C is our leading value right here. You can see it there. You can see it there. C determines our reflection and also our vertical compress or stretch. So we'll say reflect about x if it's negative. And then these rules, they're just like our A value rules, but you can see we've already got an A being used right here. So C is going to replace it just for these, but it's the same rules. When the absolute value of this number is less than 1, so usually like a fraction or a decimal, that will vertically compress our graph. And when the absolute value of C is greater than 1, so it could be 3, 4, 5, or any number bigger, it could be negative 3, 4, 5, any number bigger. As long as the absolute value is greater than 1, it's going to be a vertical stretch. Now, this new unseen before capital B. It determines our horizontal stretch or compress. Sorry, I can't write. Horizontal stretch or compress. And it's got very similar rules to our A, but everything is opposite. The A value, if its absolute value is greater than 1, is a stretch. But in this case, our B value, if the absolute value of B is greater than 1, it will horizontally, so that means side to side, it will horizontally compress. Horizontally compress. Then, if our absolute value of B is less than 1, so this would be, where it could be a decimal, could be a fraction. Even with a fraction, you got to be a little careful. You got to make sure the absolute value is less than 1, but that would be a horizontal stretch. So you can see where these are similar, very, very similar rules. They just do the opposite. And just to cover that again, C less than 1 is a compress, but a B less than 1 is a stretch. C greater than 1 is a stretch, but a B greater than 1 is a compress. So the rules are really similar, just slightly different. And through practice, you'll probably be able to pick up on those really quickly. The following examples, I'm going to do just a couple of them to save some time, and then I'm going to jump to 6 because I want to make sure that we get 6 done. Let me make sure it's still number 6 on these notes. Yeah, 5 and 6. All right, so let's look at 1. 1 is, to start off with, exponential. So you should go ahead and identify all the parent function first. So the parent of this is y equals 2 to the x power. And you can see we've had some changes done to it. We have an h value and we have a k value. And remember, h is responsible for shifts, and they do the opposite of what you would think. So when I have a -1 inside there, it's going to move my graph to the right 1. And the +3 at the end moves my graph up 3. So while you're graphing this, the kind of key things are the horizontal asymptote, which I am putting here, all right? Horizontal asymptote, which is h, a, and the critical points, which if we go look back up at the top, our critical points for exponential are 0, 1, and 1 base. So 0, 1, and 1 base. Those 3 things are all going to be affected by these transformations. So this first point is going to go right 1 and up 1, 2, 3. This point is going to go right 1 and up 1, 2, 3. And my horizontal asymptote goes left and right forever, so the right 1 doesn't really affect anything, but it is going to go up 3 also, and it will now be located right below those new points. It will be located at y equals 3. Y equals 3. Let me write that a little nicer. That's our horizontal asymptote. And then we would just graph it by creating that line that goes through there and smoothly starts to curve up. So not too bad. The critical points, like we said, they were 0, 1, and 1, 2, but after the transformations, the up, down, and the left, right will affect these. If it goes right 1, that 0 will become a 1. If it goes up 3, that 1 will become a 4. And then same thing here, we're going to go right 1 more, and we're going to go up 4. So we have, up 3. So we'll have 1, 4, and 2, 5. The domain is still all real numbers, and the range is now 3 to infinity because our horizontal asymptote moved, and we have a horizontal asymptote at y equals 3. I'm going to jump down to 4 now, just so we can see something that uses ln. Okay, just something that uses ln. Remember, ln just means log base e. And our critical points for this, all right, our parent, let's start with that. Our parent would be y equals ln x, and our logarithmic critical points are 1, 0, and base 1. Well, in this case, we just said our base is e, so we would have 1, 0, and e, comma 1. Now, e is going to be something that you're going to have to approximate. It's, remember, about 2.718, and it goes on. But 2.7 gives us a nice little number to estimate on. So our critical points of our parent graph would be 1, 0, and e, which is about 2.7, so close to 3, 1. And now we only have one transformation. And it is up 1. So both of these points are going to bump up by 1, and this will give us our new ln function. All we did was take that original and bump it up 1. Our critical points, like we said, of our original, they're 1, 0, and e, 1. But all that's going to be bumped up 1, which is going to affect the y value. So it's going to now be 1, 1, and e2. 1, 1, and e2. Our domain, it still doesn't touch 0, but it does go right forever. Our range, this graph goes up and down forever. So it'd be negative infinity to infinity. And the asymptote in this case is vertical. It's x equals 0. X equals 0. All right, let's jump down to 5. Find the inverse. Inverse method it's been unchanged this year. To find the inverse, you swap x and y, solve for y. And at the end, you're going to write it as the inverse function of x. So let's do that with this given function. So we have f of x, which is y, equaling 2 plus log 4 of x minus 5. So we first want to take the x and the y and actually swap them. And now we've got to do all of the inverse operations to get rid of everything surrounding this y. So the first thing we want to do is subtract 2 from both sides. We want to get that 2 moved over. So that gives me x minus 2 equals log 4 x minus 5. Now remember, a log is an operation. It is an operation. So to cancel it, we need to do its inverse operation, which means I'm going to take both of these. See, it's a log base 4. I'm going to take both of them, and I'm going to make them exponential with a base of 4. It's the inverse operation. Now, sorry, I wrote that as an x. Let me make that a y. So now, if you know your exponent rules, you'll know that when the base and the base of the log match, they cancel. And so that leaves me with 4x minus 2 equals x minus 5. I keep writing x. It is a y minus 5. And so ultimately, we're trying to solve for y. So the last thing we need to do is add 5 to both sides. And we would get 4 to the x minus 2 equals, plus 5 equals y. And instead of writing that as a y, we would actually want to then replace it with the negative or the inverse function of f. Inverse function of f. That would be our inverse. And I have written so large, and I have cut into my space for problem 6 that I'm going to clear this and move on. Now, this is a big problem. This is one that asks for everything, okay? It asks for everything, so we got to do everything. Now, the kind of weird part about this one is it has been transformed, and we have an h value, we have a base of 4, and we have a plus 3 out front, and that can be a little confusing because it is our k value. We're just used to seeing it at the end, but it doesn't change anything being in the beginning. It's not a horizontal stretch or compress. It's not a vertical stretch or compress. It's just our k value out front instead of at the end. So our parent function here, our parent would be log base 4 of x. Our critical points would be 1, 0, and base 1. 1, 0, and base 1. So that would be our parent. Let's go ahead and graph that out now. 1, 0, 4, 1. And it's logarithmic, so it would kind of go this direction. Sorry, I'm trying to make this like dotted and temporary, and it's just looking worse. All right, so now we need to actually transform that. And to transform that, we would look at that h and that k value, and it will be moved left 2 and up 3. Left 2, up 3. So that means both of these points will go left 2, up 3. So that point that was 4, 1 is now 2, 4. And that point that was 1, 0 is now negative 1, 3. So those points have been moved, and this new graph still, one thing here, there's an understood vertical asymptote here for the parent function. That also has to move left 3. So we'll have this new, left 2. We'll have this new asymptote right here for this graph. It's got to also move with the function. And so we go down here. Let me use a different color. We go down here, we get super close. We curve over here. We continue increasing just at a much slower rate. And that's our original. So now let's answer some questions about it. The domain of it. It goes from negative 2, not included, to the right forever. So positive infinity. For range, it goes up forever and down forever. And so we would say that it has a range of all real numbers. It has a vertical asymptote at x equals -2. And now we want to graph the inverse of it. The inverse would mean that we take the original we are going to swap our x and y. And then we're going to slowly move everything over to be on the other side so that we can isolate this x. To get rid of the log base 4, I'm going to make it exponential with a base 4. I'm going to do that on both sides. Those will cancel, and it will leave me 4x minus 3 equals y plus 2. And then my final step is going to be subtract 2 from both sides. And that is my inverse function of x. And now I want to actually graph that one. And that's a parent y equals 4 to the base power. And I have transformed it with my h and k. I have moved it right 3 and down 2. Moved it right 3 and down 2. So if we take that original parent right here, our critical points for it would be 0, 1, and 1 base, so 1, 4. And I will graph the original in yellow, 0, 1, 1 base, 1, 2, 3, 4. Okay, so those yellow points in this kind of yellow wiggly line are my original exponential. And you can see that yellow and that blue are inverse of each other. They reflect over the line y equals x. But now we have to transform this yellow graph. So we have to take the 2 points that we are kind of basing everything off of, and we have to move them to the right 3, 1, 2, 3, and down 2. And to the right 3, 1, 2, 3, and down 2. And we also have to move, we have like an understood horizontal asymptote here. Sorry, that was right below where I wanted it to be. We have like an understood horizontal asymptote here that also has to move down 2. So instead of being up there at 0, it's going to bump down here to y equals -2. And now we can graph this. I'll graph it in green. It will go way over here, and it will curve through these points and curve upward. Now remember, inverse functions should reflect over the line y equals x. So if I start at my origin and I make a line with a slope of 1, and I go all the way through the corners, that's the line that they should reflect over. Inverses should reflect over the line. Y, don't know why that keeps happening. It's very laggy today. Y equals x. And if you look at this function, the pink one, and this function, the green one, they do reflect each other over that line. So the last questions we're going to be answering here are about our teal or green function. The domain is going to be all real numbers because it goes left and right forever. The range is going to be -2 to infinity because it has to stop at that horizontal asymptote. It doesn't go below it, doesn't ever cross or interact with it. It does have a horizontal asymptote at y equals -2. We already graphed it, and the transformations listed out here of these final 2. We have a number out front and a number out front of our input. So this one is a C value. This one is a B value. Look back at your rules and you'll see that when the absolute value of C is greater than 1, that's going to be a vertical stretch by a factor of 3. When the absolute value of your capital B is less than 1, that's going to be a horizontal stretch. All right, guys, for this last one on 6b, there are two transformations. One comes from this 3, which is a capital B value, and one comes from the 2 inside parentheses, which is a lowercase h. You could say, like, if it told you that the parent of this function was a base 2, you could say that it had a C value of 2, which would be a vertical stretch. But probably just assume it's a base 4. This B, having an absolute value greater than 1, would be a horizontal compression. And this 2 would be a horizontal shift. And remember, the number inside the parentheses does the opposite of what you think it would do. So it's going to go to the right 2.